So to kind of update ourselves from 8.3 here, what happens when this isn't just log, when it's not log base 10, when it's something else? What we're typically going to do here is we're going to use some critical points, but they have a little bit more flexibility. You'll notice the 1, 0 is still going to be here as one of my values. But I need to come up with some other ones. And I'm going to show you how you could do it on the calculator if you wanted to. But I'm also going to show it how you can crank this out without having to do that. This 1 over b and this b comma 1 basically are based off the premise that my log's base in this case is 3. So when I'm going to make my critical points, I'd have a critical point at 1/3 -1, because 1 over 3. I'd have one at 1, 0. Okay, unless you have a left or a right shift, that won't move. And then B1, which would be 3, 1. Now, can I come up with a sketch without doing this? Sure. If I wanted to type it into the calculator and let the calculator help me out, because I'm trying to go a little bit quicker and I'm not wanting to necessarily remember all of those, I can go to y equals. And what I would type in is I'd do a change of base on this, which basically is I would take the log of what normally would be my physically larger term. It's my of term, but in this case it's x, and I'd divide it by the log of my base. So if I was going to type that here, it would look like that. Log of x divided by the log of 3. And what would happen is, when I go to do my chart, so there's my error, which typically it would. It's not going to move my asymptote at all, because you'll notice when it graphs, my asymptote's still going to be at x equals 0. So that's nothing different. I still have my point at 1, 0. I see the point at 3, 1. The nice thing about doing it manually is you get this extra value to help you remember, oh yeah, this is just going to keep going down and down and down. So when I go to graph this, and I get my points in, it helps remind me, oh yeah, when I'm making my curve, it's just going to keep coming down like this. Hopefully that also helps you remember when you're trying to get your other information that your asymptote hasn't moved from the y-axis from when your asymptote would just be x equals 0, which it would be for this one. And it also doesn't change anything else. It doesn't change my domain, which is just my asymptote value to infinity. And it doesn't change my range, which is going to be negative infinity to infinity. Those types of things don't change at all, and since I didn't have to play with a y-intercept, excuse me, an x-intercept here, because I see my y value there is 0, so my x-intercept is still straightforward. So really there's not a whole lot of difference between these and the base 10s. The main difference that you're going to find is just going to be whether you want to go to the calculator to get the points or if you want to use these generic critical point values to make your graph. Because even if you just had gotten these 2 points from the calculator and sketched it from that, your graph's going to be close enough to being correct that I'm not going to sit there with my microscope going, oh, that curve isn't quite going, sharp enough, quickly enough. And I wanted to make sure we talked about that. Okay, I'll quit yammering now about it. Are there any other ones, whether they're graphing or not graphing, thank you, from the homework that we want to take a peek at? Yes, sir. Number 10. All right. So on 10, I'll keep that there for a minute. So 10, 10 graph. Okay, I just want to make sure. I'm looking at my C210s. Okay, 10 graph. Let me flip this. Keep the hot sheet available. All right. So we've got 4 times the log of base 4 x minus 6. There's a couple of things I can figure out before I even start playing with the calculator. One of them is that I've got a shift working this time. What's this minus 6 in the parentheses? What type of shift is that going to be? Okay, so it's going to be, in this case, it's going to be right 6. So what that does, because remember, my vertical asymptote is going to be at 0 unless I have a right or a left shift. So here, since I have a shift to the right, my asymptote is also going to move to the right. So my vertical asymptote would end up being at 6, which also tells me my domain is always going to be my asymptote value to infinity. So I know that part. My range is always the same, even if I shift and move things around. So that's okay. The question is, how do I get these other values? So let's see, maybe by using the calculator for a little, we can kind of figure out how we might be able to do this manually, because we haven't talked about how I deal with that coefficient in front otherwise. So you're like, now wait a minute, what's this going to look like? This is the one that gets a little bit trickier. So I'm going to have 4 times, and you're like, ew. And here's the part that gets a little interesting. Okay, I want 4 times all of this. So the question becomes, can I just do, let me get it typed in first and then we can chat a little bit. My change of base, you're like, ooh, that's a lot of stuff to try and keep track of. Did I just put one too many parentheses in? I think I did. Yes. So basically what I would be doing, and I have to be careful of, is without making this a parenthesis like I did here, because that's a common error that people make. The calculator is going to do 4 times the log of this and then divide it by this. But you're looking at it and going, well, that's not what this says. It's 4 times that. So what I'm going to do, now we get to keep track of all the parentheses. Okay, here we go. So I want the log of x minus 6 divided by the log of 4, okay? That takes care of it if I didn't have these 2 parentheses in. These two, their purpose is to say I want this whole thing with the logs being divided, this part, done first. Then once you come up with that answer, now I want you to multiply it by 4. So there's a lot of things for me to be thinking about here to make sure this works out okay. So once I do, and I graph it, I notice a couple of things. You're like, okay, we shifted to the right 6, but then, ooh, this is kind of going, whew. So let's take a look at the table and see what we get here. So you're like, okay, I've got a point at 7, 0. I've got a point at 8, 2. And I have a point at 10, 4. So I'm looking and I'm going, now how is this making any sense? Because if I just took my base, which is 4, this one we don't see as much. But then I start looking at this and I'm like, right 6, that'd make that 7, 0. Okay. So I see where, oops, let me get my calculator out of the way. I see where this is coming from. Because if I shift this point right 6, that's 7, 0. I get this. So then I look at this one and I'm like, okay, my B is 4, so 4, 1. But I shifted it right 6. So that'd be 10, 1. Oh, but I multiply it by 4. So the Y value is what's getting multiplied by 4? Right. So that's the thing that gets tricky about trying to do all of this mentally. My suggestion for most of you is going to be, if there's a coefficient in front like this, that you let the calculator help you come up with the extra points. Because you will notice, even when you look at the picture of it, it shifted to the right 6, and my asymptote's still in the right place. So all of this information worked, and that's why I always like to do this before I even start dealing with the calculator. Because now, when I do go to sketch it, I can go ahead and plot the points, which I hopefully just gave myself enough room. 2, 3, 4. Yeah, I'm going to squeeze this in. And I can get my asymptote in. And have all the values that I need to be able to find my solutions. This is more the exception to the rule. Most of the ones you'll notice that you were dealing with may have a change of base, may have a shift, but typically aren't going to be having to deal with that stuff on top of it. If you want to play the mental math with it, you can, but that's just a whole lot of things to keep track of. If you're keeping track of these, letting the calculator help you with the points is not a bad thing. Yes, sir? Now, the x-intercept, good question, because I forgot we had one more part to this. So your x-intercept, again, is when y equals 0. So since I have a value when y equals 0 is 7, my x-intercept would be at 7, 0 on that one. Other issues, because those have all been good questions so far. Okay. What we're going to do today is we're going to go a little bit back towards the world of algebra a little bit more and away from the graphing. So for the moment, let me move this to the side. This is more like going into puzzle solving mode with these. These are kind of fun. So we're going to actually solve some equations today using some of the properties of logarithms that we've talked about a little bit so far. So here's basically what we are going to be attempting to do. And I do notice we got one thing, I kind of got shortcutted here a little bit, so I don't want to do that. Couple of quick examples at the top before we get doing ours. Solve the log of base 2 of 2x equals 3. One thing that you would notice, I hope, right away is I would need to get that log base 2 away from my 2 to be able to solve it. This is different. Once it has the x with it, I can't just be like, yeah, be like, no, it doesn't quite work. So what I'd have to do to both sides to get from this step to this one, which I didn't put in here, is you'd be exponentiating both sides. In other words, you'd be turning both of these into exponents where your 2 and your log of 2 are inverses, which would get me to this step. And then, of course, from there it just turns into an algebra problem. 2 cubed is 8. Divide by 2. So my x value would end up being 4. So I'm using some logarithm function properties to get rid of the logs so I can actually do the regular algebra. But these will be the ones that you're going to like the most. If you have logs of the same base on both sides of an equation, okay, basically that means what's in the parentheses has to be equal. Oops, no x. So you're just going to take, in that case, if they're both log 2, I just set those equal and go algebra equation on it. And find a solution. So if it looks simple, probably is going to be with these. But those are the two types of situations I can get myself into on this. So like for instance, I could look at this and say, okay, let's see. Now 32, wait a minute. Can I take 2 to some power and get 32? Yes. This is really log base 2 of 2 to the 5th. So we're going to start using some of those little rules that we had before to make this work a little easier for us. Because then I can wipe those, and this is really just 5 equals 3x. And I can divide by my 3. So all of those tools that we got from the last section, whether it be looking at this and knowing, 2 to the 5th gets me to 32, 2 to what power gets me to that base of, and working it that way. Now, is that always going to work? No. Sometimes stick a variable in. When that happens, we go back to exponentiating. I want to get rid of a log base 3. I'll use the 3 to exponentiate. Because the 3 and the log base 3 are inverses. What's 3 to the negative second equal? 1/9. Because again, it's 3 squared, which is 9, but it's its reciprocal. So I'd flip it over. And then please be cautious. On this last step, when you divide by 2, when you're dividing a fraction by 2, it's like multiplying by a half. So don't go the other direction on me. Don't go 2/9 on me. It's going to be 1/18. Because again, when you're dividing, you're having less of it. You're splitting it into a smaller piece. And don't leave it as 1/9 divided by 2. Simplify, simplify, simplify. This could be interesting. Anybody have an idea how they might tackle this? We haven't dealt with something besides just a number or just a variable term down there. You're like, let's see here. How could we do this? I keep waiting for somebody to come up with one of a couple of possible plans here because I'm flexible. I just don't want to force you into something. Ideas? No? You're going to leave it to me? They're like, yes. Okay. I can exponentiate something like this. I can take my 2 to the x and still do it this way. If I do, those would still be inverses, so I'd still get my 16. But now I have this quantity 2x that I'm taking to the negative second. So what's this going to look like? Not only do I take its reciprocal, but I also have to send that squared all the way through. And now it becomes the deal of trying to figure out how I'm going to get x by itself. This may take an extra step more than I'd like it to, but that can happen sometimes depending on how we solve the problem. Since my 4x squared's in the denominator, the only way I can get it out of there is if I multiply both sides, because then at least I can get it out of that spot. 4x squared times 16 get me 64x squared. And now there's actually some light at the end of the tunnel here. I can divide by 64. You're like, holy cow, Hardy. And square root it. Lovely. What's my end solution going to be? I think I heard it. 1/8. So you're like, wow, we're starting to see fractional stuff come up everywhere. That's the idea, that we've got the ability to be able to do that using these. But as you see, exponentiating for the most part is going to be how we deal with this stuff right off the bat. And some of you, it's just going to be getting back to understanding how these exponents work. Like, for instance, what's 25 to the 1/2 equal? And not 12.5. What's that?
Just 5.
Just 5. Because 1/2 is just a fancy way of saying the square root of. And then multiply both sides by the 2. Now, they're not always going to be, I was going to say, sometimes they do get easier. It's not like they're all going to be big, crazy, complicated. But again, whenever you see those logs with a base, we're automatically going to be thinking this way. But keep telling yourself you're exponentiating. This is an exponent now. So it's not 4 times 2, it's 4 squared. And then we just work our way through the steps to get but your skill sets on all of these with exponentials is going to get tested a little. And I'd challenge you, even if you use the calculator on some of these, sometimes try to make yourself go through this and not use a calculator. Like, I think this one's a good example of being able to do that. Remember, we're always doing exponent over root. So you're like, okay, so I do the root part first. The cubed root of 8 is 2. And then the exponent would be 2. So 2 squared is 4. Could I just type 8 to the 2/3 in my calculator? Yeah. But again, challenge yourself when you're given an opportunity to. And it'll make these go even faster when you get going along a little bit further. Now, 7. We've been rolling along so much with exponentiating everything. You might think about doing it here, but I think that could get kind of ugly because I really don't want that to be my exponent. So we come back over to here for a minute. 3 to what power is 243? 5. So that's where just simplifying what you have can make things a lot easier on you. It's just using a different tool. And again, just keep reminding yourself when you're doing these type of problems, and I'll actually do it completely out on this one. When you get into something like this, what you're basically doing is saying, okay, I want this to be something that's a base 6. Bless you. So 6 to some power gets me 216. And by doing that change of base, those just take care of each other, and I can get to my answer. So whether you look at it as 3 to what power is 243 and you get it, or instead of looking at 6 to what power is 216, you just change the base and then look at it this way, you're doing the same thing basically. It's just how you choose to go after it. But those are the tough ones. Left the easy ones for last today. Both sides of your equation, if they have the same base, you just set whatever's in the parentheses equal to each other. Now it doesn't mean some factoring may not get involved, because if I've got x squared, I always want to bring all of my terms over to the x squared side so I can go ahead and factor this. So I can get multiple solutions. Now what I may do occasionally on something like this, especially when I see it for a first time, because, you know, curiosity can get to be there a little bit on something like this. Especially I get a little bit leery when I look at negatives here. So I look, and if I plug this in, I'm actually going to check one here for once. So I'd have -2 squared minus 6. Now I don't want to put all that in my calculator. And we're not going to. We're going to simplify this. So negative 2 quantity squared would be 4. 4 minus 6 is negative 2. So I'm like, okay, log base 2, negative 2. And then here, oops, if I learned how to copy correctly. You're like, oh, okay, I feel better about this. I actually can see that the two sides are equal. But even if I didn't do it that way and I wanted to check, I could do log divided by log. Uh-oh. Error, non-real answer. Wait a minute. Let's go to this. Cal, why is this doing this? Let me show you why this is doing this. See, I don't do these things by chance. If I were to just graph the log, and it was just 2 to the x, so I was just doing log of x divided by log of 2. I wasn't worrying about all the other shifts and things like that. I was just graphing that, okay? When I go to graph it, do any of my x values go left of 0? No, there wasn't any reason for them to. So here's my dilemma. When I get negative numbers that would go in here, those are going to be part of the table when I get to error, okay? Because they're imaginary. I can't graph them. So when I get into a situation like that, I do have to take a minute to make sure it's not making it negative. Because if it does, that solution isn't going to work. The positive numbers will, as long as it keeps the value inside there positive. But whenever we get a negative log number in there, it's just not going to work. So you do have to be a little bit careful on those. They are easier, but you just have that extra little something to keep track of. I'm going to come back to 10 in just a second because I want to do one more like this while we're doing them. Same log base. Maybe we'll get life a little easier on us this time. 4 would be 11, would be 11. That's all good. So we don't have to worry about this one. But then we get to the last one. And it's like, what exactly would you want me to do on this guy? Well, let's see. Let's find something similar and see how we might tackle this. Could tackle it sort of like that and do x plus 4. Ooh, but then I got to cube it. Do I really want to do that? Well, we might get stuck doing it. Let's try it. So if I exponentiate with x plus 4, an actual quantity this time, okay, those would wipe each other. I think somebody will come up with something in a minute and go, couldn't I have just, but we'll see. So 27 equals x plus 4 to the third. Yuck. Do not multiply this out. How can I get rid of that cube? Cubed root it. But at least the cube root of 27 is something that comes out nice. Subtract my 4, and I get negative 1. Now, when I stop to think about it for a minute, I'm like, you know what? I might have been able to make this a little easier on myself. Because when I look at this, I'm like, negative 1 plus 4 is 3. Oh, 3 cubed is 27. I really could have just asked myself, how do I turn this into 3? Because 3 cubed is 27, which may have made it a little simpler. But we got there still. It wasn't terrible. So, over the next, 3 months before I see you again, I'm like, they got plenty of time to get this situated. So the problems at the done are kind of the bottom, not the done, the bottom, give you an opportunity to kind of practice and play with this a little bit. When we do come back, there are going to be a couple of review type things that we do too before we get to that quiz whenever we actually get to that. So then that's why I also gave you that other little test prep sheet with some questions on it, just to get you some more practice at doing what we've been doing already. So by the time I do see you again, you haven't completely forgotten everything like you had winter break. Oh, wait a minute, you kind of are, with what's going on with these. Videos and things will be up, and like I was telling a couple of people, we're going to push back the